As referenced in my previous videos, crystal growth occurs in a liquid solution as the solution evaporates, and the physical properties of the crystal, such as size, cohesiveness, and clarity, are affected by whether or not the appropriate particles are in place in the structure of the crystal. If there are many contaminant particles in place in the structure of your crystal by the time all the solution has evaporated and the crystal formation process has stopped, the resulting crystal may not have a high level of clarity because the contaminant particles affected the light diffraction throughout the crystal, as well as disturbing the links between the particles of the crystal, meaning your crystals may look like many smaller, non-transparent crystals rather than one larger crystal with a high level of clarity and quality. To maximize clarity and quality, we can consider the qualities of equilibrium as applicable to a saturated solution. If the equation for a reversible reaction is written where aqueous reactants yield the product, which is the crystal in our case, and if we want our crystal to have more clarity, we need to keep the solution at a point where the rate of particle swapping is rapid enough that impurities can be swapped out before the crystallization process has completed. This may mean that we need to keep the system in equilibrium, which is a sort of middle point where the solution is neither tending too much towards a state of being a liquid solution and not tending too much towards being a mostly crystallized form, where not much more growth or swapping is occurring. At equilibrium, the system should be at a point with an optimal swapping rate. This can be done by ensuring that the solution is adequately saturated with alum, because a watered-down solution will only slow the process without doing much for the crystal growth. This is because it'll take longer for the solution to evaporate without much more medium from which crystals can grow. You should also ensure that there is an optimal amount of solution in the vial. When there's too little solution, the dry environment is not optimal for the particles to swap. If there's plenty of solution, the process will be slower, but as long as the solution is saturated and you are willing to wait it out, this can produce a high-quality crystal where the appropriate particles have plenty of time to swap into place in the crystal structure. D-spacing is the distance between planes of atoms in the regular structure of a crystal. Differences in D-spacing will affect the visual properties of the crystal, such as color, because different D-spacing leads to different ways in which the crystal and its structure interact with light. The periodicity of a crystalline structure is one of its identifying characteristics. We can find more information about the properties and structure of a certain crystal by performing some calculations with the equation 2d sine of theta equals n lambda, which signifies the relationship between wavelength, which is lambda, the distance between the planes in the structure, which is d, the difference in path length in the lower path of light, which is n, and the angle at which X-ray light passes through the planes, which is theta. Using this equation and the powder X-ray data for alum, we can calculate the d-spacing for alum's diffraction pattern at the most intense peak on the plot. We know that our n value is 1, and based on our plot, we see that our wavelength value is 0.15418 nanometers, and our theta value is about 20.6 degrees. Using our equation, we can then calculate the value of d, which is the distance between the planes in the unique structure of the alum crystal. To calculate the value, we can first manipulate the equation to isolate d, which is the value we're solving for. This gives us the equation d equals n times wavelength over 2 times the sine of theta. Now we can plug in our n, wavelength, and theta values. This gives us d equals 1 times 0.15418 all over 2 times the sine of 20.6 degrees. This can be simplified to 0.15418 all over 2 times 0.35184. This is then equal to 0.15418 all over 0.703683. This value is equal to 0.2191042, and this can be represented in scientific notation as 2.191042 times 10 to the negative 2. This is our value for d in nanometers. This value represents the d-spacing in alum crystals, which is unique and characteristic to alum, and the way that light diffraction occurs in crystals of it. There haven't been any environmental changes for my vial of alum crystals thus far. We see that there's definitely been more crystal growth, but it does seem that the bulk of the crystal growth had occurred between videos 1 and 2. Since then, the rate of growth seems to have slowed down. As explained earlier, this may be because of the decreased amount of solution, and the crystal thus may be nearing the end of its growth process in terms of the amount of solution that we've added to this vial. The volume of solution left in the vial is indeed much less than the volume that we had seen before. At this point, the crystals are fairly large and fairly clear, so I would consider my attempts to grow alum crystals fairly successful.